Today I discuss one important topics which is related to norm space and convex set and many more. Okay, so we start from this definition of norm space. Okay, first we give definition of this. Let X be a vector space. Let X be a vector space over field K, over a field K, and n x to r and n x to r be a function, be a function. Then n is said to be a norm. Then n is said to be a norm on X if first one, norm of X greater than equal to 0 for all X belongs to X, and second one, norm of X equal to 0 if and only if X equal to 0. Third one, norm of Cx equal to C mod of C norm of X for all X belongs to X and C belongs to K. And here 4, norm of X plus Y less than equal to norm X norm Y. Okay, for all X Y belongs to X, then this is one function defined by norm. Okay, one function which is norm of X. Okay, define norm on X, norm on some space. Then we discuss about that. Here we write norm space. Okay, that means X norm is defined as this norm space. Okay, then we write if X equal to Rn, then norm xp equal to summation I equal to 1 to n mod of xi whole to the power p whole to the power 1 by p. This one is norm of xp, and in this way we also discuss here x difference y p equal to dpxy equal to summation I equal to 1 to n xi difference yi whole to the power p whole to the power 1 by p. Okay, 1 less than equal to p less than plus infinity. Then norm of x infinity equal to maximum of 1 less than equal to I less than equal to n norm of xi. Okay, maximum of this. Then we're also going to be the definition of additive, subadditive, and positive homogeneous function. We also known about it, but today we discuss this. We erase that portion now. Now we're going to further discussion of that. Okay, so write some definitions now. Also talk about some definitions here. Okay, then also write here, let X be a real inner product space. X be a real inner product space. X norm, then this one is better, or X inner product, then this better. Otherwise we call it just X, then X be a real linear space. Okay, a real linear space. If real linear space, then not a problem, these definitions are work. Okay, and if x to r be a function, then f is said to be additive. F is said to be additive. First one, additive if f of x plus y equal to fx plus fy. Okay, for all x y belongs to x. Number 2, sub-additive if f of x plus y less than equal to fx plus fy. Okay, for all x y belongs to x. Number 3, positive homogeneous. Okay, when we write positive homogeneous, if f of alpha x equal to norm of alpha f of x. Okay, when alpha belongs to k and x belongs to x, then we'll call it this one. We'll write these definitions. Now some observations we write here. Okay, if norm x to r is sub-additive, then and if norm have two property, we write here norm is sub-additive and positive homogeneous. Okay, we write this definition of norm and obviously satisfies these two property, norm sub-additive and obviously norm is positive homogeneous. Okay, next we talk about where is that portion and going to the definition of convex set. We known about it in previous class also or previous section, but today we also discuss now. Okay, convex set. Which set is called convex set? First we talk about now convex set. We write this definition first. Okay, let C be a non-empty subset. Let C be a non-empty subset of a real space X, non-empty subset of a real linear space X. Okay, real linear space X. Then C is said to be convex. Then C is said to be convex if xy belongs to C. This implies that 1 minus tx plus ty belongs to this C, or t belongs to 0, 1. Okay, open. Then C is said to be convex. Okay. Now we're going to, that means another definitions of affine. Okay, we know about it. Then here we'll talk about if this one hold or if t belongs to holds to the or 1 minus tx plus ty belongs to C, for t belongs to closed 0, 1, then not a problem at all. Okay, next we talk about here C is said to be affine if xy belongs to C. This implies 1 minus tx plus ty belongs to this C, for t belongs to A. Okay, then we write now convex function. We also erase that portion and going to the definition of convex function. Okay, I write here now convex function. Okay, convex function. Let C be a non-empty convex subset of a, non-empty convex subset, non-empty convex subset of a real linear space X, and if C2R be a function, then f is said to be convex, then f is said to be convex, if f of 1 minus tx plus ty less than equal to 1 minus tf of x plus tf of y. Okay, x y belongs to c and t belongs to 0 1. Okay, then what we talk about next, this one is convex function. Next we give some example here. Okay, example we talk about if x equal to x square, then this one is this one we choose it. If fx, then f of 1 minus tx plus ty equal to this one 1 minus tx plus ty whole square. Okay, then what we say about it? Okay, there is certain, that means we also check it here. 1 minus t square x square and t square y square plus 2t 1 minus t xy. Okay, and here f of 1 minus tx equal to f of 1 minus tx equal to 1 minus t square x square, and here f of ty equal to t square y square. Okay, then there is certain problem, that means here this one is not, if we satisfied this, then this one is not convex, I think. Okay, because here this one less than equal to 1 minus t fx, sorry, there is not 1 minus t here. Okay, there is just fx. Okay, fx equal to x square and fy equal to y square. Okay, then this one is, that means 1 minus t fx and 1 minus t fy equal to y, right here 1 minus t fx plus t fy equal to 1 minus t, okay, 1 minus t x square plus ty square. Then there is some problem, then which one is larger we don't know. Okay, so this example is not gives this one is convex or not. Okay, now we also talk about, that means next, every norm is a convex function, or erase that portion. That means this one just an example, will not talk about this one is convex or not. Okay, next it is that portion and going to further discussion of that, which one every norm is a convex function. Let we write here every norm is a convex function. Every norm is a convex function. Okay, let xy belongs to x and t belongs to 0 1. Then then norm of 1 minus tx plus ty less than equal to 1 minus t norm of x plus norm of ty equal to 1 minus tx plus ty. Okay, this one. So we also do that. Okay, that means every norm is a convex function. Okay, then we also do that every norm is a convex function. Okay, this one satisfies convex condition. Next we also talk about here x square. We don't know, but now we're also going to one theorem. Okay, we write this theorem here. Let x be a linear space, x be a linear space, and let if x to r be a function, x to r be a function such that first one, if be subadditive, if be subadditive, and second one, if is positively homogeneous, if is positively homogeneous, positively homogeneous, then f is convex, then f is convex. Okay, now we write this proof here. Okay, let xy belongs to x and t belongs to 0 1 and t belongs to close to 0 1. Since f is subadditive, since f is subadditive, then f of 1 minus tx plus ty less than equal to f of 1 minus tx plus f of ty equal to 1 minus t f of x plus t f of y. Okay, then this one be ap subadditive. Okay, then we have to prove f is convex. That means this one obviously satisfies this condition. Subadditive means this one, then obviously this one. So f is convex. Okay, since positively homogeneous, so here we use positively homogeneous, then f of 1 minus tx equal to 1 minus t common in fx. So this one becomes, so we write here, so f is convex. Then this one is just that if subadditive and positively homogeneous, then this one is a convex set. Okay, convex function, if subadditive and positively homogeneous, then this one be a convex function. We now erase that portion and going to be now let C be a non-empty subset of a matrix space XD. Let C be a non-empty subset of a matrix space XD. Non-empty subset of a matrix space XD for x belongs to x define f of x equal to dcx equal to infimum of y belongs to c d of xy. Thus f of x to r be a function and fx difference fy less than t into x difference y for all xy belongs to x. Hence f is continuous. Hence f is continuous. Okay. So we also now discuss another differentiability of convex function. We write this one in theorem prop. We also, that means, write this statement here. Okay. Differentiability of convex function. Differentiability of convex function. Let U be an open convex subset. Open convex subset of Rn. And if U to R be a convex function, such that f is differentiable, at point C belongs to U, then fx difference fc difference f dash c multiplied by x minus c is greater than equal to 0. Okay. Now we also proof of this theorem. We erase that portion. We now write proof here. Let x belongs to u. And t belongs to 0, 1. Hence f of 1 minus tx plus ty, f of 1 minus t, c here, not xy, here c we write, and tx, okay, these 2 points. Then this one less than equal to 1 minus t f of c plus t f of x. Okay. Now this one f of c t x minus c less than equal to 1 minus t f of c plus t f of x. Set u equal to x minus c. Then f of c plus du difference f of c less than equal to T f of x difference f of c. This implies f of c plus tu difference f of c by t less than equal to f of x difference f of c. Okay, this marked as 1. Note that f is differentiable. F is differentiable, then f test cu belongs to R. Now subtracting f test cu, both sides we get f of c plus tu difference f of c by t difference f test cu here tu by t less than equal to fx difference f of c. Here's f dash difference f dash cu. Okay, now erase that portion and going to further discussion of that. F of c plus tu difference f dash c difference f dash c tu by t less than equal to f dash x difference f of c difference f dash cu. Okay, note that f dash cu equal to f dash cu taking limit as t tending to 0 we get okay 0 less than equal to fx difference fc difference f dash c u. So this one, that means if taking 0 we get this one. Now we write here, so this one equal to 0 less than equal to fx less than fc difference f dash c x minus c. Okay, then what we talk about that, we talk about let u be an open convex subset of Rn, and if u to R be a convex function such that f is differentiable at point c belongs to u, then this one hold. Okay, then this one is the, that means we're also going to the one important result about convex function. Okay, so we also prove today. Okay, now we erase that portion and going to fixed point theorem. Now fixed point theorem. In a complete matrix space, in a complete matrix space, every contraction mapping has a unique fixed point, has a unique fixed point. Okay, that is, let X be a complete matrix space. X be a complete matrix space, and if let f x to x be a function such that be a function such that d of fx fy less than equal to k of dxy. Okay, for all xy belongs to x, and for some k belongs to cos 0 1, then there exists a unique element x star belongs to x such that f of x star equal to x star. Okay, this one is fixed point theorem. That means a complete matrix space and a function defined by this one, this contraction mapping. Then this one is, then there exists a unique element x star such that this one fx equal to x star. We also proved this, but today we just write this statement of this theorem. Okay, so now we stop here.